Okay. Okay, Lewis. So Arrhenius's acid-base theory covers the majority of acids and bases that you would interact with. Okay. A slightly broader view is Bronsted-Lowry, and then the most all-encompassing view is the Lewis acids and bases theory. So this is the most modern one, and it basically just says, so it slightly modifies it. An acid is anything that accepts an electron pair. Okay, so all Arrhenius acids and bases are also Bronsted-Lowry acids and bases. All right, and all what? Oh dear. Yes, there's an old commercial that they used to have where they're doing brain surgery and they're trying to cure someone's seizures and they're poking around in the brain and she says, I smell burnt toast, because before she had a seizure she always smelled burnt toast. So that's why that's the thing. It's an old commercial. You could probably look it up. It's a vignette, probably made by CBC. Yeah, yeah. Okay, anyway, an acid is anything that accepts an electron pair to form a dative bond. What's a dative bond? Is it? Is that really what it is? It's, here, look. It's actually where both the electrons in a bond come from one species. Do you remember that? So in the case of, if we were going to talk about something acting as a Lewis acid, well, let's look at H plus, right? So if I take H plus, that is clearly something that's able to accept the pair of electrons, right, in what's called a dative bond. It doesn't bring any of the electrons to the table itself. So something like ammonia is a very fantastic pair for this. Okay, so this is a Lewis acid. It's a proton, or sorry, it's an electron pair acceptor. This is a Lewis base. It's an electron pair donor, right? This makes a dative bond between the hydrogen and the ammonia to make an ammonium ion. So a dative bond is where both electrons come from one species, okay? Let's just define this. There's a Lewis acid. We'll define Lewis base in notes in just a second. There's a Lewis base. This makes a dative bond, which we'll remember is both electrons come from one species. Okay? Oftentimes, if you see a dative bond, it goes like this. So it's like made with a little arrow. That's the symbol for it. Okay? And it's basically saying, I'm sharing both my electrons with you, hydrogen. Okay? So that's quite simply really the definition of a Lewis acid and a Lewis base. So all Bronsted-Lowry and all Arrhenius acids and bases fall under the heading of Lewis. Okay? So it's like an umbrella. It's kind of the ultimate, I guess, way of describing acids and bases. A little bit more, I suppose, complicated than Arrhenius's definition, but it encompasses, I think, all possible situations where something is acting as an acid or a base. So let's do another example. Let's look at the reaction between boron trifluoride and ammonia. I would. Or you can just watch the video later. Okay, so boron trifluoride, how many electrons does boron have around it? It does. And boron trifluoride is kind of interesting in that there's no octet obeyed here. Okay, so it's like this. Now take a look at that. This thing is ripe to accept electrons. Okay, and if we put it near our best friend here, NH3, you'll see that that pair of electrons is available for sharing. And what you will create at the end of the day is you will essentially have those electrons donate their way on over. And I think you end up with this, although not exactly sure. Okay, so in this case, this is a Lewis acid, and this is a Lewis base. Okay. Right. So we would draw an arrow this way. Right, so we make a dative bond. So this is our electron acceptor. I'm not sure. Is that how you spell acceptor? And this is our electron donor. Now, upon initial view of this, right, you just look at that, and you're only thinking Arrhenius. There's no way that can be an acid, right? There's no H plus to donate, right? In fact, H plus isn't even involved at all here. There's no H plus involved, and yet this still has acid character. So these species like this were noted to have acid character, right? And yet, clearly there's no way they can be an acid according to older definitions. So this is why the Lewis definition was needed. Let's try one more thing here. How about something like this? What can we say about aluminum that looks like this? And let's just remember what we have here, right? So OH kind of looks like this. Right? Does that make sense? That's what OH would look like? OH minus? Because remember what we had originally was this. And then it went to this. Right? So we have lots of electron pairs to donate, right? So so this is clearly a base. And what will happen is you can actually associate aluminum like this with 4 OHs. So in this case, actually, the ion, aluminum 3 plus, or the, what do you call an aluminum ion? I guess just an aluminum ion, right? An aluminum ion is actually considered to be a Lewis acid, okay? Which again, Bronsted-Lowry or even Arrhenius or even Bronsted-Lowry theory doesn't work, okay? So that's it. Done.